Okay. Okay, so last time I had a horrendous time trying to get bitmap fonts into an application. The first of those steps, using an app called font64, we got the hang of this eventually, even if it had its quirks. But in the second part, when we tried actually importing a PNG or just image output by this into the program, doing so with Raylib was kind of difficult. Given that in the last project, the Butterfly app, using these QOI images over the PNGs resulted in a really faster load time, and given that the specification is actually possible to read and create a decoder for in a couple of hours, unlike the PNG format, which takes weeks, I figured that long term it will be quite useful to have my own encoder, or at least my own ability, my own code that will take a embedded QOI file and just produce an array of pixels from that. And so that's what I want to do today. Okay. So yeah, I vaguely had a look at this when it was released, I think a couple of years ago, in 2022. Almost slightly over 2 years ago now. And yeah, I just want, by the end of the day, I want to be able to say, embed this file, run some code, either at comp time or runtime, and just give me the array of pixels of the corresponding image. That's all I want to do. That's all I need. Okay, so actually before we do this, it would be useful just to have a really simple image to do stuff with. From memory, there's a certain file format, which is image file format, which is really easy to do. This series, Ray Tracing in One Weekend, mentions what this is at the beginning. What is it called? The PPM image format. PPM image. So presumably ImageMagick will be able to convert something to it. Yeah, like I want a simple example like this with which to run the entire thing. Okay. So this itself should be an image. Okay, so let's actually do example.ppm. Save all of that. Okay, and now if I run ImageMagick on this, magic k example.ppm and then do example.qoi, note, okay, it doesn't like this. Let's try this one. If this one fails, we'll just manually make a basic image that has this. What's going on, Emacs? Okay, that seemed to work. Yeah, this seems to be what I want. Yeah. Okay, so now at least we've got a really basic file with which to do stuff. I don't know why this one failed. Interesting. Anyway. This should be enough to get started. Okay. So now it's time to read this and then figure out how to input this stuff. So yeah, if we, for instance, read the example2.qi format now, yeah, we just get all of this binary data. And yeah, we're going to figure out how to process this. Get rid of this and get rid of all of this. Okay, the Quite Okay Image Format by Dominik Zabulski. Okay. Consists of a 14-byte header followed by any number of data chunks and a 8-byte number. I am streaming right, yeah. So yeah, these magic width on pixels, 32. What does the B mean? Channels, this or this, color space. Okay. So one of the first things we can do is just start processing this stuff. Okay, so let's do this. So we can say const standard is equal to, how do we do this again? Import standard. Let's split the screen. And yeah, we also want to embed our test file. Const test image is equal to embed file. What was this? Example2.qi. And then we can start doing this. Main void. Let's go. Okay. So first of all, let's copy this header. So we want this to be what we have. We're gonna have to do some calculation. 4 bytes. Okay, why don't we do the length first? The byte length is going to be 4 characters plus 4 of the U32, 4 of the height. This is already kind of nasty because I'm extracting information from here out of here instead. Let's make this more descriptive. So why don't we say magic byte length is 4. Then we can say the image width byte why don't we actually do header in front of all of these? So your header, the magic byte length, and then for the header and the image byte, presumably, like, all of these are going to be in bytes. The lengths of different parts of the QI header in bytes. So yeah, the header magic length is 4. The header image width length is 4 as well. The header length image is a bit nicer. 4 as well. Then the header channel length is 1. And finally the header color space length is equal to 1 as well. Okay. So then the overall length, the QRI header is just going to be the sum of all of these. Okay, image length plus. Let's just put these on separate lines. Okay. Channel length plus space length. Okay. Okay, so now we've got that, we can actually just start processing this header information. So now we can say the QRI header is going to equal, in this case, the test image, and we want to slice it from 0 to the QRI header length. And then let's just print out what this is. Example 2.QRI. So which presumably it's this. We'll see. Let's do dprint bytes. So when we say header raw, and here we just want to say the QRI header, and then let's say that dprint here is just the standard .debug.print function. Okay. So we want to do zig run QRI.z. Unused local constants. I guess I forgot to add that in. Like, I was recently at a conference and someone was complaining that the compiler issued error messages like this. This is why you want the compiler to tell you stuff like this. Okay, that seems to be working. Let's now process this. Okay. So now we want to say the header magic bytes is equal to, let's see, what's the best way of doing this? Part of me wants to just define, since this is a really rigid format, we can literally just say the bytes that comprise, like the byte that comprises the channel is here, the byte that consists the width is here. But then this means we need to do some like intermediate sums, but doing some intermediate sums with this feels slightly tedious. I kind of want to do something a bit different. What would be, like, you're getting something that works with this really easy, but since this is my own parser, I want this to be nice. An easy way would honestly just be creating a struct that basically replicating this struct. And then this way we still, replicating the struct would be an even better way than simply just specifying what this stuff is. Okay, let's do this. So why don't we do QI header is equal to a struct. And so yeah, we're gonna have, instead of car magic 4, here it's going to be constant U8. Or how do we do structs in Zig again? Is it name and then type, or type and then name? It should be name and then type. So we can call this magic bytes of type this, and then yeah, and then we just want the image width of type U32, image height type U32, the channel type U8, the color space type U8, and then that's that done. Okay, let's clear this again. Yeah, this was the simplest thing to do. I'm not sure why it didn't occur to me to begin with. Okay. And now we want to pass this. So why don't we say pass pass the QI header into the okay, so now we want to say yeah, so now we literally just want to say that I think we can even be more we can say the magic bytes are going to equal just the what was it called? The test image. The first 4 bytes. Then we want to say that the image width bytes is going to equal a similar thing, but now from 4 to 8. Then from 8 to 16, from 8 to 12, we're going to have the image height bytes. Then the image channel I say channel type, but maybe just channel is enough. Channel bytes is going to equal, it should be channel byte equals the 9th element, and then the color space byte is equal to the 10th. No, something's really off. That looks better. Yeah, the overall sum of this should just be 14, which is not quite, which is now what we have. Okay. Now let's process these. So now we need to convert these from two of them we need to convert. Oh, actually, we don't really need to convert these at all. We can just we do. We need to convert these from, like, we need to kind of just like transmute cast these. It would be transmute and Odin, but otherwise we just need to cast these. How do we do that? We just want to say maybe we want to say given these bytes, convert it to an int. So we want to do like int from pointer. Convert an integer address into a pointer. Like, I want to convert what's at the pointer into an integer. Is this fine? At int from pointer. What does it do? Converts value to a usize, which is the address of the pointer. Pointer from int. We can see. Let's try this. So we say test1 is equal to int from pointer image width bytes, and then let's just print out what that is. Constant allowed on array child type. Okay. No, that's just literally just converting the pointer to an integer. Okay. So if we do reference, like, there is an easy way to do this, which is just to manually convert it by just saying multiply each byte by the appropriate number and move it up. There must be a nicer way of doing it though. Maybe not. What if we tried this? Oops. Bitcast must have known result type. Okay, very fair. We want this to be a U32. Cannot bitcast from constant. Okay. Slightly annoying. We might put this, I might put this on Discord afterwards. Unless there's like, do we have transmute somewhere? No. How can I do a transmute operation in Z? Oh no, we don't want to bypass the, yeah, let's, this doesn't look good. We'll do this the dumb way. We will say what do we say? We can say for let's write a new function. 4 bytes to 32. And this is just going to take in something of presumably this form and return back this. And we just want to say for we want to say like we want to cast each of these bytes to a U32 and then just shift it up appropriately. So we can say total is equal to 0, and then we want to say total plus equals we need to do endianness calculations, which I'm not a fan of. Simple enough. Once we convert it, so I want to do, can we do as and we want to say, okay, before I like repeat this, I want to see if comparison actually works. Okay, so let's say image width is equal to 4 bytes to 32 image width bytes. It's gonna work. What do, yeah, let's print this. Expected type found star const for U8. So is this going to be fine? No. I still don't understand like the nuance in like where the const goes in these fixed array types. Okay, so as is, this says what? So it's saying let's find this instead. Do I need to dereference this? Function with non-void type implicitly returns. Yeah, so we can say return total. Okay, that's okay. This is working. That's good. So now I want to say total plus equals this thing. But now we want to shift it up by 8 bits. And likewise, shift these up by 16 and 24. Okay, and was it the case that this image had a width of 6? I forget. Check it. It was example2.qi. Yeah, that looks like that has a width of 6 to me, which is good news. Okay. Likewise, we can say that the I guess we can immediately start defining what this struct is then. Okay. So now we've got these. This we kind of don't actually have to include. Likewise with these, we don't really have to do them either. Okay. So now we can say const qi header is equal to qi header. How do we do this again? Do we just say magic bytes equals this, then dot image width equals this thing, but now wrapped with 4 bytes to 32. Likewise, do this with the height. And then for the other ones, for the channel, this just equals this stuff. And then the color space is equal to 13. These are meant to be commas. Okay. Maybe that's it. And let's kind of just print this out then. So now we can just say the header of type any should be the QI header. Okay. Error line 18. Expected U8 found const for U8. Would dereferencing it like this work? No, definitely not. What do we do here? Like, what does the star even mean in the type? I don't actually know. This seemed to be working before, and then we did something, and now it's not. Like, I just want to cast this. How do we do that? Well, maybe I can just adjust it up here. But I thought when I tried doing stuff up here before, it failed. Like, this will give the child error, won't it? Yeah. Not allowed in array child type. Indeed. What am I meant to do? This is so annoying. I'm just saying it's a constant array of bytes. Here's a constant array of bytes of length 4. Maybe the documentation will help. Is there stuff working with strings here? Just copy the bytes over. That's all I want to happen. we can do this in a really crude way. It's been so long, let me just remind myself how this stuff goes in the exercises. Actually, before we do that, let's just check out all of the basic types. If I do some weird type like I1, 2, 8, just this. So how did these work again? It was like Sentinel is where we need to go. Okay, I could just define it like this. I could just say it's a pointer to a fixed array of 4. You can give that a go. QI. So what if I do that? Doesn't like it. I suspect this is going to not like me too. Well, at least we're getting an error on another one now. Slightly better. Expect to type this, found const that. Okay, so then if we say here, okay, this is good, kind of. Okay, I'm pretty sure the image height was 10. So what does the 3 mean? The 3 means this is just an RGB image, which we could check later, and 0 means sRGB with linear alpha. Whatever that means. Hopefully we won't need to do much with that part. I do want this to actually be 4 bytes instead of a pointer to it though. So let's just manually say, this is so crude, but the compiler will copy it this way. At least it's better. Oh no, 18. And the image is not good. Image, instead of test image, it really should be raw image. So let's do test image with raw image. Okay. No. Expected. Why? The compiler knows this is just meant to be 4 U8s. Do I need to define it like this? Okay. Great. And yeah, these look like character stuff to me. So maybe I guess we don't actually need to. We don't need to debug print this. It's okay. If anything, I can just say dprint. Is it the case that I guess we can print this as a string. Print the QI header dot magic bytes. We'll turn this into an assert statement later. Yeah, it's printing it as QIF. Great. What so now we want to just say check that the file is actually a QI file. Well, check the magic number, the magic bytes are correct for a .qi file. So now we say QI header magic bytes, constant header magic bytes match is going to equal the QI header magic bytes equals QI F. Yeah, which is just like as per the specification. And then we just want to assert that this is the case. Assert magic bytes match. It cannot compare strings with equals. How do we do string comparison in Zig? How do I test for string equality in Zig? Yeah, we know this. The LLM is just making this one up. We know that's not correct. So yeah, standard memory equal. I guess that's what we want to do. Let's just check. This is not totally crap. So yeah, so library standard memory.zig. And we want a function called equal. It compares two slices and returns whether they are equal. That kind of looks like what I want. So here we want to say standard.mem.equal. Use of undeclared identifier assert. Zig almost certainly has an assert. Where do we find this? Yeah, we don't want this to be, this could be, in later versions we could actually make this like a conc time assert, but there's no need at this stage. Debug assert. So is it standard.debug.assert? Standard.debug.assert. Expected 3 arguments, found 2. Oh, we need to pass the type in. Easy enough. Array literal requires address of operator blah to coerce slice type. Okay, does that just mean putting an and here? Okay, that seemed to work. So let's define a deassert. Deassert to be similar. Okay. And yeah, let's save this. Git add i sig. Oh hey two-step, how is it going? So you've said if you're going to be reading lots of integers from the bytes, you might want to make it FBS IO fixed to buffer stream from the bytes, and then use FBF reader read int u32 little. Oh, yeah, this could be useful. I mean, you can see I've done this like crude, just like literally convert all of these U8s to integers and add them up appropriately. Okay, but let's check out this library for a bit. So you're saying check out the FBS. So yeah, so in the Zig library standard FBS does okay. Not. Maybe just read in IO dot fixed buffer stream. Okay, so maybe IO dot zig. No. Fixed buffer stream. Oh, okay, yeah. Don't know why that didn't show up before. And this is line 1, 2, 3. Oh, so we need to actually go further into it. Fixed buffer stream.zig. This turns a byte buffer into an IO writer reader. Okay, and then there's a method to this called read int, apparently. Or maybe just reader. IO.reader. Okay, yeah, this we could do this. Yeah, and I suspect we might actually need something like this for the rest of the stuff. Because yeah, like at least currently we're reading the header of this QOI now. Like we've got in the magic bytes. The image in this case being example 2.qi, this thing, and yeah, like if you count all like the big squares, the dimensions of this are 6 by 10. Let's see, there is 5 at the bottom. Yeah, so this seems to be working. But now for the rest of the specification. So now we've done this part of the specification. We now need to do the rest of it. So yeah, two-step also says an FBS is a way to get access to some nice IO.reader methods. Yeah, it would be good just to see what some of these are. So yeah, not seeing them in this file, so presumably they're somewhere else. Okay, so there are also similar mem.readInt methods. Oh, okay. Let's check those out as well. Mem.zig. So if I try and do read int, oh yeah, this could be quite useful. Oh, this looks really nice. Yeah, read int slice. This is, I can completely get rid of some of my code. Okay, so this whole like 4 bytes to 32. I think we can get rid of this. Let me try getting rid of this now. Okay, so for this part here, so let us instead try read. Oh wait, hang on. Yeah. So we want read standard.mem.read int slice. The kind of type we want, U32. The bytes, which should just be this raw image, and then the endian. What is you can get the int rep of a string like this, mem.readInt u qif big. Okay. But yeah, okay, let me just look up what the data type of this endian is. Presumably it's big, like you said, but I just want to see all the options. Okay, so if we search here and do endian. Okay, built-in.zig 452. Built-in 452. Yeah, this will be just big or little. Okay. So yeah, so over here we want endian.big. But yeah, hopefully this works. Oh, hang on. We were I forget if we've saved this or not. Never mind. Zig run for i.zig. Oh, it doesn't like that. Is it going to be inferred if I do that? Okay, it will. So we were expecting 6 and 10, and yeah, it did return 6. Great. Yeah, thanks Two-Step. This is you're being extremely helpful as usual. Yeah, let's just get rid of this. Get rid of this entire thing. Not needed anymore. So yeah, likewise, we can just copy this here, and now change this from 8 to 12. Easy. So I could say thanks for the I can just say like thanks to okay. Yeah, this I feel like the best way to learn is collaboratively, and it's amazing whenever you join Two-Step. Okay. Yeah, and yeah, I'm happy that Zig is like, I wouldn't be using Zig if it were not already a systems level language. But the fact that it has all of this built-in systems level stuff that you actually want to do, well, like when you actually need it, like when you're passing a file, is really very great. Okay. Okay, yeah, but back to the where were we before? Back to the IO reader, that's right. So so where is it? Is it like the I guess io.c? No. Fixed buffer stream. Okay, yeah, so one of the methods of this fixed buffer stream is this reader, and then yeah, and then you're saying within like the reader itself has some method called like readInt or something. Okay, yeah, so this is of a type reader, and where is this defined? Oh, it's in io.reader, okay. Reader.z. Oh, I love and all of this is documented as well with comments. Very nice. Okay. Returns the number of bytes read. Okay. Self read, read all, read at least. Depreciated. Use something else instead. Rerun byte from the stream. Yeah, this looks really useful. I see, and now we're getting like the readInt little, endian or big. Great. Okay. And then I feel like we're gonna have to use this in the next part of the parsing. Oh, okay. Useful. And there's some examples as well. Excellent. Okay, very useful. Very useful. So you said you may not want to use the FBS if you're going to use the mem helpers, or if you want to keep track of the byte offset myself. I guess we'll see. It really depends on what's in the rest of this specification. Okay, let's read more of this. Okay. These color space and channels are purely informative. They do not change the way things are encoded. Great, because I don't really know what the difference in this color space is. Okay, images were encoded row to row, left to right, top to bottom. The decoder and encoder start with this as the previous pixel value. An image is complete when all pixels specified by this have been covered. Pixels are encoded as a run of the previous pixel, an index into an array of previously seen pixels, a difference to the previous pixel value in this, or full RGB or RGBA values. Okay. This is like ringing a bell from when I saw this 2 years ago. Okay, so I guess this option is just, this is what the value is, but this is, this would be terrible for compression. Like doing this is not compressing it at all. So these then will get used a bunch of times. And then maybe run just means like very close to the previous one. Okay, we'll see. Okay, the color channels are assumed to not be pre-multiplied with the alpha channel, whatever that means. Okay, a running array 64 of previously seen pixel values is maintained by the encoder. Okay, that means me. I mean decoder. That means me. Each pixel that is seen by the encoder and decoder is put into this array at the position formed by a hash function. This better be a simple hash. In the encoder, if the pixel value at the index matches the current pixel, this index position is written to the stream as this. Oh, like this is already like out of my comfort zone, but that's good. Like this is how we become better programmers. We push through something that we initially go, this is going to be hard. Okay, the hash function for the index is blah. Okay, this is a very simple hash function. We can write that when necessary. Okay, each chunk starts with a 2 or 8-bit tag followed by a number of data bits. Okay, interesting, but yeah, we will deal with this. We will deal with the 2-bit tag. The bit length of chunks is divisible by 8, i.e. all chunks are byte aligned. All values encoded in these data bits have the most significant bit on the left. The 8-bit tags have precedence over the 2-bit tags. A decoder must check for the presence of an 8-bit tag first. Okay, the bytes. Okay, I'm just like I want to just see an example immediately because I already. Okay, we will get through this. We'll get through this. Okay, so yeah, the byte stream is marked with 7 null bytes followed by a single 1. Okay, the possible chunks are as follows. Okay, these must be the bits. Okay. The alpha value remains unchanged from the previous pixel. Okay. Oh, sorry. Yeah, sorry, I didn't see. Yeah. Yeah. Literally, I got this specification from the QIIformat.org. Then this file format specification here. Oh, there's also an audio. I didn't realize there was a quite okay audio format. When we do audio in games, I think I'll be using this one as well. Okay, good to know. If it's as nice as this one. And I'm saying nice because hopefully by the time I understand this, I will be correct in my assumption that this is nice. Okay. Okay, so yeah, so we have these chunks. Okay, so yeah, an indication that you just have like a very specific RGB value is just, what is this? 254 values, and then, or just 255 values. Okay, and then index, 6-bit index into. I'm gonna just invert the screen since this is really bright. Okay. A valid encoder must not issue 2 or more consecutive index chunks to the same index. Okay. Yeah, so we've seen these ones, and I guess this index must be this part here. Okay, so then we're keeping track of this with 2 to the 6, which is 64. Okay, yeah, so yeah, 64 pixels, and then okay, what's the other one? So we've done that, done this. A difference to the previous pixel value in RGB. Okay, this tag, and then Okay, we are allowed to do negative numbers. So negative, I'm surprised but like happy that this image format like compresses almost as good as PNG. Like I guess it goes to show how in so many images the kind of difference between consecutive pixels is really just these values just differ by -2, -1, 0, or 1, and that itself is kind of enough to save time. Okay, and then what's the final one? The run of the previous pixel. What's this Luma? The alpha value remains unchanged from the previous pixel. Oh, what's this? This is this looks complicated. The green channel is used to indicate the general direction of change and is encoded in 6 bits. Okay, the red and blue channels base their diffs off the green channel difference. Okay, the difference of the current channel values are using a wraparound operation. Values are stored as unsigned integers. Bias of 32. Okay. Yeah, okay. Okay, this is finally the run ends up here. Okay, so there's like two kind of different ways of storing differences. So what's the difference between this one and the Luma? Presumably this is if the alpha isn't changing at all, or maybe just if the difference is small enough that it can be expressed in this way, but this is what happens if the difference is larger. Okay, and then for the run, how does this work? It's just first 2 bits are 1, and then okay, repeating the previous pixel. Oh, okay. Okay, so they're possibly, if it's an image where 64 of the pixels are just the same in a row, 63, yeah, wait, why is this 1 to 62 instead of, okay, that makes sense, No, that doesn't. Okay, so there's 63 numbers here, and then I guess, yeah, there's 63 possible numbers that can be stored in 6 bits. Okay. Yeah, note that these are illegal as they are occupied by these tags. Okay. Okay, where do we begin? This is going to be a challenge for me, to say the least. But this is actually a compression scheme that I can hold in my head at once. Yeah, this feels pretty intuitive, component-wise. Overall, not so intuitive, but it will be in time. Okay, I need an example. So let's check out one. QOI decoding example. And yeah, I don't want to like look at source code of someone who's already written a decoder. I want to try and do this myself. Like if I write this myself, I will remember it more. And then, byte. Okay, maybe the Wikipedia page has a example. It does not, it just copies everything in here. Unfortunate. Maybe there's a link to something that does. Okay, there is a video, and I'm pretty sure I watched this many years ago.
Hey, got a sec?
That. Don't need that anymore. Yeah, like, from memory, like a lot of this like beginning video was like PNGs and stuff. We don't want. Where's the stuff we actually want? Here it is. Jesus. Okay. The subtitles. No, why are they automatically generated? No. Oh wait, that website looked good. What was that webpage? Okay, let's copy this. Okay, it losslessly compresses RGB and RGBA images. Oh, there it is. Great. Okay. Oh, okay. It's I mean, this is still great. Like 650 lines in C is way better than the 20,000 or whatever the PNG format is. But I don't want to do that. I want to see an example and then figure out how to code it myself. Yeah, the format is quite okay. If there's not a simple example out there, we could try making one ourselves. Like I could just make, say, like a 2x2. I could just make some. Say it's like a 3x3 image where we tried all of these, where we have like a run of a pixel of a different color, we slightly vary the RGB values, we switch to something new, and then we just end up looking at the bytes of the QI thing itself. Because I'm also doing this just to learn an image format, so I don't, go back to this. Here's a blog. Someone's done it in Rust. Someone has done it in Zig, but I don't want to read it just yet. Yeah, I kind of just want to make some examples and just really check out the hex and see how that hex maps onto this stuff. So I think one of the nice things about this format is that each of these segments is a multiple of a byte. Like this is 1 byte, this is 1 byte, 2, 1. So this will make just looking at the hexadecimal a lot easier. Yeah, why don't we Let's make some really crude examples. So how do I make this canvas like 2 by 2, for example? Like image properties, 2 by 2. Okay. Oh, come on, like Microsoft, why can't I zoom in more? Why can't I do arbitrary zoom? Annoying, really annoying. Okay, so let's make this like red, 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 and then blue or something. Okay. So let's save this as, let's make a new folder. QRI tests. So this is called red, 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 blue. Let's convert that to QRI. QRI tests. Red, 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 blue, red, 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 blue, red, QRI. Okay. And now I want to look at the hex of this. I know it's possible to do this in Emacs because I've seen someone do it, but I've never done it myself in Emacs. So we will figure this out. So yeah, QRI tests QRI. Okay. A lot of this is just numbers. How do we view this in hex? How do I view hex in Emacs? Hexel mode. Okay, this command converts the file's context to decimal and lets you edit it. Okay. Okay. Hexel find file. Find file. And then, no. Okay, and then if we do, yes, we do. Yes. Okay, great, here it is. So I guess this is what we want. Okay, I don't know what this thing at the top is, but okay. Oh, okay, this is just the hexadecimal. This is a key. Okay. Okay. It's been Windows, like Windows can go away. Why is this here? Oh, it's so annoying. Go away. Okay, so back to the specification. Okay. Okay, so yeah, these bytes are like, each of these is a byte, and the first 14 were the header, right? Yeah, 4, 8, 12, blah blah. So this, then the size of the, can I highlight it this way? A bit sad, but okay. So yeah, these 4 will be the height, the width of the image, which is indeed 2. Then the height, which is also 2. And then the channels. I'm being really silly. These, it's been a while. Two adjacent things here form a byte. That's right. Okay. So yeah. So that's the QRIF. Why is that the width? I don't know. QOIF. 1, 2, 3, 4. The width, the height. 4 here is the channel, so this is an RGBA, and then 0 is sRGB with linear output. Okay, and then this is where the actual image data is. Okay, so now we want to say, let's just remind ourselves what this image is. Paint will be unable to view it. We want to do rrrb.qi. This thing. This is what it looks like. How do I? Let's make a new. Okay, this is what we're doing. Okay, let's just keep it here to remind ourselves. Okay, so the very first couple of things are what? How does this start off? So I guess this is going to be a chunk, so we need to figure out what chunk this is. So if it's an F and an E, that means what? It means 4 ones and then 1 1 1 0. So that looks like this chunk. Okay, so then we should expect this to, if this is a chunk, it's just going to describe this top left pixel, which it should be, everything in reds is 1, then it's 0, then it's 0. So this should then be like FF 0 0. Oh, hang on. Yeah, it should be FF 0 0 0 0. Oh, but we get something different. We get ED. Okay, I think this is because Paint, the default color. This is because let's edit this in Paint and make sure it's actually the proper colors, the colors that we want. Okay, it has already opened this one. Let's do something easy. Let's do something easier. Let's just make something that's red. Actually red, and where's the fill? Is this like the bucket? Okay, and then let's make something that's completely blue. Let's replace that. Of course I want to replace it. Let's convert it again. Okay, and now we want to reload this. Revert buffer. Yes. Oh, Emacs, what are you doing? Yes, just kill this. What was this again? So we do ML hexel mode. We absolutely don't want that. Hexel find file. rrb.qi. QOI tests. rrb.qi. Okay. This again, this is not what I was expecting. I thought I was expecting to see a bunch of FFs here, but we're not seeing those. What's happening? Okay, I'm now confused. We've got the QIF here, the width, the height, RGBA, sRGB with linear. Why do we now have 5AAC1? What header is that? Okay, so 5A is going to be 1, 0, 1, 0, 1. So I guess 0, 1. Then, wait, what? How can we be at a different byte when we haven't even set what the original one is? Confusion. What's the confusion? Okay. Also, just using like this default paint to edit this is really annoying. I kind of want a better pixel editing program. Low spec pixel editor. Only works on. I did see someone develop something like this in Zig. We might try that out. Like, this is already going down a rabbit hole, but this is not the last time we're going to be doing stuff with Pixel. Okay, absolutely not that one. Yeah, let's Zig Pixel Editor. Oh no, this is already this is too complicated. It's too complicated. Okay, I'm still just confused. Why is this as a 5A? Why is it this? Why are we getting this? I'm just afraid Emacs is doing something dumb. Let's just quit everything. Quit everything. And I just want to add in what I've done so far. Started writing QI parser. And let's go back into the QI tests. So yeah, we've got this, and this does look like the correct amount of red and blue now. Okay, and then Axel mode. Okay. So let's just take some notes. So yeah, so for the 5AC1, this means 0, 1, 0, 1. And A is 10, so that. C is 12, that. And then 1 is just that. Okay, so yeah, this indicates that it's a diff. Didn't know it could differ from nothing, but okay. Okay. But actually, okay, this does make sense. If it's starting off with 000255, then the red is going to be going backwards 1. Okay. So at the start, the decode Are we like doing the like? I'm manually doing this like decoder, but it doesn't matter. It doesn't matter. The start is 0, 0, 0, 255. Okay. So this means, yeah. So this means QOI up diff, where here the dr, dg, and db is going to equal 1, 2, and 2, and okay, and then how do we now use these to get to 255? Yeah, so then the next value we want should be this. The question is, how do we use this information to get from here to here? So okay, so these 2's must correspond to 0's. Why? Okay, since if the range is -2, -1, 1, okay, so we can say range is -2, well, possible dr values is going to be -1, it's going to be this. So then if we consider this to be an array, as in literally just consider this to be like, then we can totally see here that if you take like the second element of the array, you get 0, and then likewise if you take the first element of the array, you're going to get -1 that then takes us from 0 to that. Okay. Okay. This is making more sense than I thought it would. Okay. So then we get to here. Great. And then so now we need to do the next line. So the next line is 7900. Okay, what's this? So 7 in hex is 0111, 9 is 1001, and we get 0000000. Okay, and what op is this? What starts with 01? Well, another diff, which surprises me. Oh, I don't know. I feel like I made a mistake. How? No. I'm fine. I'm a bit surprised then. That it's another diff instead of like a repeat or a run. I was kind of expecting this to be 1-1, but okay. QI op diff, and then what are the values here? So these are now going to be 3. Right, so something's wrong. Isn't something off here? Like, surely something's off. Because like did I convert this wrong? And 7 is 0111, yeah. Okay. We'll push ahead. 3, 2, and 1. So then this says that we should be getting. We need to do the array conversion. The array. Oh, okay. Maybe it's actually going down instead of going across. Because then if it's going down, it's going to be pushing it up by 1. And then this array 2 here is going to be 0, so no change there. And then the array 1 is going to be -1. Okay, so then this is going to give us add 1 to 255, get 0. Add 0 to 0, get 0, and then do -1 to 0, get 255. Okay. So this then gives us the blue pixel, red pixel. So the next one should probably be the red pixel, I think. Oh, okay. So two-step has a suggestion. Did you see this? The difference to the current channel values are using a wraparound operation. So 1 minus 2 will result in 255, while 255 plus 1 will result in 0. Yeah. I guess that's what I'm doing, unless I'm doing something with the order that's incorrect. I'm just assuming that each time when you calculate the difference, you just add. We basically just add these values to whatever was in the previous one. And yeah, in my case, if I'm adding 1, 0, and -1 to each of these, then I get 0, 0, and 255. Okay. Okay, so that's that done. So now we have just some null bytes, and then what op does this correspond to? So this corresponds to an index. So now we have our QOI op index. And okay, the index is just going to be these values here, which is 0. Okay, so now we need to go back into the yeah, and then two-step says, yeah, wrapping add slash subtract in Zig plus percentage sign and minus percentage sign operators. Right, yeah. But from memory, like Zig also gives you errors if you get a runtime error if detects overflow or something from memory, unless you say otherwise. Okay, so yeah, so we have this index of 0, and then because secretly so far we've been keeping track of this running array of previously seen pixel values. Each pixel that is seen by the encoder and decoder is put into this array at the position formed by a has function of the color value. Okay, so I guess we need to add in this to these calculations. In the encoder, if the pixel value at the index matches the current pixel, this index position is written to the stream as index, which I guess is what we're doing now. I'm still trying to work out what's happening with this running array. Okay, so yeah, if we're trying to decode this, the very first one we see is this, and so where does this get stored in this array? So we need to hash it. Okay, So let's just do this calculation. So now we say like new, so hash. Okay, and then, so now we want to say the index position is equal to the red, 255 times 3 plus 0 times 5 plus the blue 0 times 7 plus 255 times 11 subtract 64, and what is that? So 255 times 3 plus 25. Okay, we can do algebra. We can simplify this. Adding 3 lots of 255 to 11 lots of 255 is just 14 times 255. So, 255. Okay, and then we want to quotient this 64. Let's just do this the really basic way. Okay, so we got like 50 or 54, which is 50. Okay, so that's where that's ended up. And then, okay, and then when we get this blue pixel, we also get something new. So now the index position is equal to a similar thing. Okay, 0 plus 0 plus 7 times 255 plus 11 times 255 mod 64. So then this is going to be doing our algebra again. Where is it? 18, right? It should just be 18. Yeah, 18 times 255 minus 64. Do it the dumb way. Who cares? 46. Okay. Okay, but then what's happened? What has happened at this stage in the calculation? We now have gone. We've gone like, remember, this is what it looks like. We've gone. Well, now I'm confused. How did we go from red to blue? What? I'm so confused. Are we starting at the top right and going down, or are we starting at the bottom and going across? I don't know. Point is, there's 2 more pixels left, and okay, and we're doing this like op index thing again. Okay, so a valid encoder must not issue 2 or more consecutive index chunks. Run must be used instead. Okay, so but I don't know what's going on. It's saying the index here was 0, but these values have been stored in 50 and 46. Unless it was like, unless it was something here. Okay, yeah. A running array of previously of pixel values is maintained in both directions. Each pixel that is seen by the encoder is put into this array. Yeah. In the encoder, if the pixel value at the index matches the current pixel, this index position is written to the stream as index. Like, I'm not sure what this means. What does this sentence mean? So maybe it just means if the current pixel is in this array, write out that number. Okay. But then why are we getting this position is 0? And why are there like extra bytes? Like this represents blue, and then this is another byte here that should represent like a repeat, an extra pixel. This should represent a repeat, like an extra pixel. So then why are there, what are all of these ones at the end doing? Yeah. Okay, bye two-step. I'm probably gonna go to bed in like 20 minutes anyway. But I've already learned a lot today. This is, we've made progress so far. Okay, what could be wrong? What's going on? So yeah, we start here, got the red, got the blue, got the red. Oh, is it, okay, this doesn't make that much of a difference, but yeah, instead of 790 here, it should just be 79. This is just a single byte. So then we end up with the next byte, which is 00. Yeah, and now it's still the same confusion. I am confused. What's going on? So yeah, it was red, blue, repeat, repeat, massively empty bytes. Unless like part of this is just like padding because of like Windows, possibly. That. No, I don't think so. Could I have like stuffed up this hash, or like I feel like I'm not understanding exactly how stuff goes into this index completely. Yeah, like I'm not expecting to see zeros. I'm expecting to see 50 in hex, but we're not seeing that. Oh, it's the C1, I think. Maybe this C1 is actually doing repeats. Hang on, yeah, because I'm such a noob. Okay, yeah. So 5A, which is the QI diff, single byte. So the next byte after this is C1. At least I've got this far, despite it being midnight, in my defense. Okay, so C is 12. So 1, 0, 1, 0, 0, 0, 0, 1. Okay. And now we end up with what? Oh, this like Luma. This is not correct. This is 12 in hexadecimal. Okay. So now now we do end up with a run. Great. This is much better. QI OP run. And now 6-bit run length repeating the previous pixel. Okay. Yeah, so then we end up with, oh yeah, this is really good. So yeah, so okay, the image does look like it's going from left to right, top to bottom. So now we want to repeat this pixel twice. So what does that, what do we expect to see then? We expect just to see the number in here representing 2, and we need to kind of offset this somehow. So let's just decode it. So we can see the run here is equal to literally 1. So then the run length is stored with the bias of -1. So presumably this just means you need to add 1 to it. Stored with bias of 1, so add, so run plus equals 1 gives 2. Okay, so then we end up with 2 of these. Okay, then we end up with 7, 9, which is the blue pixel, and then at that stage we're done. After that it's just zeros because of like padding by Windows. Okay, cool. We have successfully decoded this manually. Let's adjust it a bit. Let's see. Let's just like, I want to increase this run first off, and what else could we do? I also want to use this index notation. So what if we like have some red, then have some blue, and then go back to red again? This would, and then go back to blue again. This would actually we want something really different that actually forces this to get used. So in order to do that, we need a color that is sufficiently different. So if we did something that was gray, we're not going to be able to jump to that via +1 or 2. Okay. So yeah, let's do a similar example. And then we'll call it a night. Actually, let's save all of this. Let's save all of this. So let's add the QOI, and let's add the rb.text. added notes for manually decoding a simple qi2.qi file. Okay. So yeah, let's do one more. Paint was okay provided we set the colors ourselves. So let's instead make this 3 by 3. Okay. Let's make everything bright red first. Okay. And now now we did want to alter this a bit. So now we want to say, let's have like a run of 4. And then let's do like a gray. So for gray we can do like 8, 8, 8, 8, 8, 8. Do that like in the middle. And then let's adjust to blue. Okay, and let's do gray at the... We can do like gray at the end as well. But we'll swap to blue. So yeah, swap to gray, and then going back should be like an index, and then swap. Actually, maybe we'll do red, blue, ... Okay, this looks good. And I can't use G because that would be green. So what is this going to be? Red, blue. Let's do X for gray. Red, blue, X. .png. Okay. Let's convert this. Magic K. Red. Blue, X, red, blue, X. QI. Okay. Okay, and now let us open this up. And we want to do, is it like hexel mode? Yes. Okay. Bed very soon, but before that, let's just see if this kind of makes sense given what we've seen. So yeah, the magic number, then the width, the height, the width which is 3, the height which is 3, RGBA mode, linear, and then 5A which was the red, like last time, C1 which was the repeat 3, like last time, and then this time we transition to the gray. And so yeah, so when we transition to the gray, we've got 7, 9, which corresponds to what? In hex, this is 0, 1, 1, 1. Oh, wait, why are we getting a diff? It shouldn't be a diff. Because we swapped from like 0 to like 8, 8, and wait, what? Yeah, we can figure this out tomorrow, but okay, something weird, and then back to red. So then FE is 1, 1. Wait, what's happening? I was kind of, I wanted this, I wanted us to see this, but we're not seeing the index being used. So you got red, 2, blue. Oh, wait, I was being silly. The 7, 9 is the blue, that's fine, that's the diff. Okay, then we end up with FE, and so FE is still 1, 1. Well, it's now 1, 1, and so then we're... Oh, no, yeah, where it's... Oh, this is going to make decoding it a bit annoying, actually. Yeah, because this is what I do. How are we going to distinguish between this and this? Okay, then we do get the 888 colors here. This is the gray color. Okay, yeah. Let's just finish decoding this in our heads. Okay, so then we get the gray, and then the red again. So 3, 2 is now 0, 0, 1, 1. Aha, we have successfully got the index. So 0, 0, 1, 1 gives 3. Why has the red been stored in 3? I thought it was meant to be stored in that, which is not 3, 3 in hexadecimal. Oh, I know. This is kind of complicated, actually. So this is 0, 0, 1, 1 space 0, 0, 1, 0. So we've got 1, 1, 0, 0, 1. Okay, that is going to be a largest number. That actually does kind of look like 50. Okay, presume that's 50. Then what? Then we want another, either like another index or just another difference. We've got 2e instead. This looks like it is another index, even though it could be a diff, since it's another 0, 0. And then we're repeating b. So instead of a, I guess it could be a run, because it's a C. But a C is 12, which is 1, 1. Yeah, okay, yeah. So then we repeat it once, which is what the 0 does. Then we're back to gray. So then we look up the index again. Okay, yeah, cool. This is good. Okay, yeah. I feel like I want to conclude. Let's save this, and then we'll conclude the stream. I'm going to add all of the QOI files. Add another simple. Okay. And there's heaps of font map. Okay, there's heaps of font stuff here, but we'll get to this eventually. It's not now. Yeah, like the stuff last time is gonna all be redone. Okay. But this is good progress. Okay, so now we've now created some examples, and I'm now where we've decoded these manually, and I'm now kind of feeling confident to actually just start implementing this now. The only tricky part seems to be distinguishing between these two. it's annoying that both of these start off with 1, 1. We're going to have to think about this. But yeah, unique to recognize, unique to recognize, unique to recognize. And then here, oh, I guess this is why this part down here says it's illegal. So I guess we then, if the first 2 bits are 1, 1, we then look at the run. If the run is just that, you go, okay, it's the operation is RGBA. Otherwise, if it's not this, it has to be that. And then you go, okay, it's really, you examine, you check to see if it's these. Okay, this is okay, great. I'm excited to do this tomorrow. I feel that by the end of tomorrow, or possibly the day after, I will have created a working QRI decoder. And then we can just immediately read in any QRI file into a byte array and then start using that in our app. And you know, not to diss on C completely, but I'm gonna bet that my implementation is significantly less than less in size than this one. Where was it? Okay, granted this has a lot of comments. Okay, I take my claim back. If it starts at line 300 and ends at line 600, I feel like mine will probably be between 200 and 300 lines. Okay. Yeah, sayonara, and probably see everyone tomorrow.